At Mach 2, jet engines have a fundamental mechanical problem. If supersonic air hits the spinning compressor blades of a turbojet, the aerodynamic shock will instantly choke the engine, stalling the airflow and shutting down the power plant in the middle of the sky. To solve this, aerospace engineers in the 1950s had to figure out how to slow the air down to subsonic speeds before it reached the engine face. The Soviet design bureau Mikoyan-Gurevich solved this with a brutal, purely physical mechanism. They placed a massive, heavy metal cone directly in the center of the aircraft's nose intake. As the jet accelerated past the speed of sound, a mechanical actuator literally pushed this metal spike forward out of the nose, altering the geometry of the inlet to manage the shock waves. It was an incredibly effective aerodynamic solution, but it dictated a catastrophic operational compromise. By putting a giant moving metal spike in the nose, they left virtually no room for a radar dish. They deliberately sacrificed the pilot's ability to scan the sky, see beyond visual range, or hunt autonomously. They traded situational awareness for raw, cheap straight-line speed. This bizarre engineering choice perfectly encapsulates the central conflict of the MiG-21. It was not designed to be an independent, multi-role fighter aircraft. It was designed to be a manned, reusable surface-to-air missile, built to fulfill a distinctly Soviet mathematical equation where absolute numbers and simplified logistics completely overrode crew survivability or systemic independence. How did a jet so technologically stripped down, so aerodynamically compromised, and so ergonomically hostile manage to dictate the terms of aerial engagement for decades, forcing NATO to rewrite its entire combat doctrine? The answer lies in the uncompromising brutalism of its engineering. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. To understand why the MiG-21 looks and flies the way it does, you have to look at the aerodynamic paradox of the 1950s. Designers were frantically trying to push past Mach 1.5, but the swept-wing designs that had dominated the Korean War, like the MiG-15 and MiG-19, were hitting a structural and aerodynamic wall. Swept wings at high supersonic speeds suffered from massive wave drag and severe aeroelasticity. The wings would literally twist under the aerodynamic loads, occasionally reversing the effect of the ailerons. The Soviet Central Aerohydrodynamic Institute, known as TSAGI, conducted massive wind tunnel testing campaigns to find a shape that could punch through the sound barrier with minimal resistance while remaining rigid enough to survive the stress. The answer they handed to the Mikoyan-Gurevich Bureau was the delta wing, a triangle. But adopting the delta wing immediately created a nested loop of engineering problems. A delta wing solves the high-speed drag problem beautifully. Its leading edge is swept back steeply, keeping it safely behind the shock wave generated by the nose of the aircraft. Structurally, the root of a delta wing is incredibly wide, meaning it can be built exceptionally strong and rigid without needing heavy internal bracing. In theory, this massive triangular volume also provides ample space for internal fuel tanks. The designers of the MiG-21 eagerly adopted the delta shape, but the pursuit of absolute maximum speed drove them to heavily modify it. To reduce drag to the absolute minimum, they made the wing incredibly thin. A thin wing generates less drag, allowing the relatively low-thrust engines of the era to push the airframe to Mach 2. But the price paid for this ultra-thin profile was severe. The internal volume of the wing shrank drastically. Instead of being a flying fuel tank, the wings of the MiG-21 could barely hold enough aviation kerosene to keep the jet aloft for an hour under normal conditions, and mere minutes if the afterburner was engaged. This fuel restriction forced the aircraft into a very specific operational box. It could not patrol, it could not loiter. It became a point defense interceptor by sheer aerodynamic necessity. It was designed to sit on a runway, wait for a ground controller to spot an incoming bomber formation on massive ground-based radars, scramble, climb at a dizzying angle, make a single supersonic pass to fire its weapons, and immediately return to base before the fuel gauges hit zero. But the aerodynamic compromises of the delta wing did not stop at fuel capacity. A pure delta wing, like the ones used on the French Mirage series, lacks horizontal tailplanes. Elevators on the trailing edge of the main wing handle pitch control. But AGI knew that delta wings suffer from a vicious center of lift shift when transitioning from subsonic to supersonic flight. The nose wants to pitch down aggressively. To counter this, the trailing edge elevators on a pure delta must deflect upward, creating tremendous drag and killing the aircraft's acceleration. To solve this, the Soviet engineers broke from the pure delta design and created a tailed delta. They kept the triangular main wing but added a conventional swept horizontal tail section at the rear. This gave the MiG-21 phenomenal pitch authority at supersonic speeds, allowing it to muscle its way through the sound barrier without burying its nose or bleeding off all its thrust. However, this gave birth to another brutal consequence at the other end of the speed spectrum. Delta wings generate lift at low speeds by creating massive vortices over the top of the wing, but this requires flying at a very high angle of attack. The nose must be pointed steeply upward to maintain lift at approach speeds. Because the MiG-21 had a tailed delta configuration, the heavy tail surfaces and the complex airflow interactions meant the low-speed handling was notoriously unforgiving. When a pilot brought the MiG-21 in for a landing, they had to maintain a high speed and a high nose angle. If they dropped below the critical speed, the thin delta wing would suddenly stop flying, completely stalling without warning. The jet would simply fall out of the sky like an anvil. The resulting landing speeds were terrifyingly fast for a 1950s airframe, requiring heavy-duty pneumatic brakes and a mandatory deployment of a drag parachute to keep the jet from rolling off the end of the runway. These aerodynamic characteristics were intrinsically linked to the propulsion system, which required just as many brutal compromises. The heart of the early MiG-21 was the Tumansky R-11 turbojet, later upgraded to the R-25 in subsequent variants. The Tumansky engines were marvels of Soviet brutalist engineering. They were essentially hollow tubes filled with spinning blades that converted vast amounts of air and fuel into raw thrust. They were not particularly fuel efficient, nor were they exceptionally durable, but they were incredibly easy to manufacture, simple to maintain in primitive conditions, and generated a staggering amount of power for their size. But getting that air into the engine brought its own set of mechanical nightmares. As an aircraft approaches Mach 2, the air entering the intake is moving faster than the engine compressor blades can physically process. If supersonic air hits the compressor, the aerodynamic flow breaks down, the engine surges, and thrust instantly disappears. The air must be slowed down to Mach 0.4 or 0.5 before it reaches the engine face. This brings us back to the nose cone, or the translating center body shock cone. When the MiG-21 is flying below Mach 1.5, the cone is fully retracted into the nose. The air flows smoothly into the annular intake lip. But as the pilot pushes the throttle into afterburner and the jet accelerates past Mach 1.5, sensors detect the pressure change. A mechanical system automatically pushes the heavy cone forward out of the nose. When the supersonic air hits the tip of the extended cone, it creates an oblique shock wave. As the air passes through this shock wave, its velocity drops, and its pressure increases. It then hits a second normal shock wave just inside the intake lip, slowing down completely to subsonic speeds before traveling down the long internal ducting to the engine face. It is a highly efficient way to manage supersonic flow, ensuring the Tumansky engine has a constant supply of dense, high-pressure subsonic air regardless of how fast the airframe is moving. But the cost of this intake design was catastrophic for the avionics. By occupying the entire front of the aircraft with a massive air intake and a moving metal spike, there was virtually no real estate left for radar equipment. The designers were forced to cram a tiny, primitive radar set into the limited volume of the shock cone itself. In the early models, and later in the widespread MiG-21 PF and BIS variants with the RP-21 Sapphire radar, the antenna dish was so small that its performance was borderline useless by modern standards. It was essentially a glorified flashlight. On a clear day, with zero ground clutter and a massive target like a B-52 bomber flying straight and level, the radar might pick it up at 12 miles. Against a fighter-sized target, the pilot would be lucky to get a return at 6 miles. The radar was also completely blind looking down. If an enemy aircraft was flying below the MiG-21, the radar would only see the reflection of the ground. This lack of onboard situational awareness shifted the entire operational burden off the pilot and onto the ground-controlled interception, or GCI, network. The MiG-21 pilot was not a hunter. He was a trigger puller for a radar operator sitting in a dark bunker miles away. The ground controller, looking at massive early warning radar arrays, would track the incoming enemy and radio-precise headings, altitudes, and speeds to the MiG pilot. The pilot was expected to fly blindly to a point in space dictated by the controller, only turning on his pathetic nose radar at the last possible second to achieve a lock and fire his weapons before diving away. This severe reliance on ground control heavily influenced the design of the cockpit, which was less of an aerodynamic workspace and more of a hostile work environment. Visibility out of the canopy was famously terrible. The heavy metal framing of the canopy, combined with the high spine of the aircraft, meant the pilot could see almost nothing behind him. The forward view on landing was equally obscured by the high angle of attack. Inside the cockpit, the ergonomics were a chaotic sprawl. Switches and dials were scattered wherever there was empty panel space, with little regard for workflow during high-stress combat. The interior was famously painted a stark, bizarre shade of turquoise green. Soviet aviation psychologists had supposedly determined that this specific color reduced stress and kept pilots calm during intense operations. An ironic touch, given that fighting in a MiG-21 was inherently a high-stress exercise in fuel starvation and visual blindness. The pilot was strapped into a crude ejection seat, surrounded by a cacophony of pneumatic hisses, managing a fuel gauge that dropped visibly by the minute, waiting for a crackling voice on the radio to tell him where the enemy was. So, after seeing how it actually performed, do you think the Soviet design approach of trading radar capability for pure intercept speed was worth it? Let me know in the comments. When the theoretical math of Soviet design met the dirt of real-world combat in the skies over Vietnam, the brutal reality of the MiG-21's engineering was fully exposed. The United States entered the Vietnam War confident in its doctrine of qualitative superiority. NATO air forces were built around massive, heavily armed, radar-equipped interceptors like the F-4 Phantom II. The Phantom was a technological marvel, an enormous twin-engine missile truck designed to detect enemies from dozens of miles away and destroy them with radar-guided Sparrow missiles before a dogfight ever occurred. But the thick, humid skies of Southeast Asia nullified the Phantom's technological advantage. The early Sparrow missiles were notoriously unreliable. The humid environment degraded their electronics, and the complex radar locks often failed. Furthermore, strict rules of engagement often required American pilots to visually identify targets before firing, completely negating the Phantom's beyond visual range advantage. The North Vietnamese Air Force, operating under strict Soviet doctrine, used the MiG-21 exactly as it was designed. They did not attempt to engage the Americans in turning dogfights. The ground controllers would track the incoming American strike packages using early warning radars. They would vector the tiny, hard-to-see MiG-21s into position above and behind the American formations. The MiG-21's tiny cross-section made it incredibly difficult to spot visually, especially against the dark jungle canopy. A flight of MiGs would dive out of the sun at supersonic speeds, blowing right past the heavier American fighters. In that brief window, the MiG pilot would fire a K-13 Atoll missile. The K-13 was actually a direct, bolt-for-bolt, reverse-engineered copy of the American AIM-9B Sidewinder, acquired after a Chinese jet returned to base with an unexploded American missile lodged in its airframe. It was a heat-seeking weapon that required the MiG to be directly behind the target, looking at the hot exhaust. The MiG would ripple-fire its missiles, punch through the American formation at Mach 1.5, and immediately dive for the deck, using its phenomenal acceleration to run away before the heavy Phantoms could turn and pursue. The North Vietnamese pilots were effectively utilizing the high-speed, hit-and-run tactics the airframe demanded. The math was working. A cheap, aerodynamically compromised, short-range interceptor was successfully harassing and occasionally destroying multi-million-dollar technological marvels. It took the United States an agonizingly long time to realize that a cheap dart could neutralize a complex missile truck if used correctly. The losses forced a complete re-evaluation of American air combat training. The U.S. Navy instituted the Top Gun program to relearn the lost art of dogfighting, while the intelligence apparatus worked desperately to get their hands on a real MiG-21 to figure out its weaknesses. They finally got their chance through a highly classified exploitation program known as Havdonut. In 1966, an Iraqi pilot defected to Israel with an almost brand new MiG-21 F-13. The Israelis eventually loaned the aircraft to the United States, where it was secretly flown against every fighter in the American inventory out in the Nevada desert. The American test pilots evaluating the aircraft discovered the real-world cost of the Delta Wing design. The MiG-21's acceleration was terrifying. Its initial turn rate was excellent. But the moment the pilot attempted to sustain a hard, horizontal turn, the Delta Wing acted like a massive air brake. The jet bled off airspeed at a catastrophic rate. An F-4 Phantom pilot who could survive the initial pass and drag the MiG into a sustained turning fight would watch the Soviet jet lose all its energy, wallow in the sky, and become an easy target. The evaluation also exposed the immense physical strain on the pilot. The heavy, unboosted flight controls required immense physical strength to manipulate at high speeds. The lack of a sophisticated gun sight meant that if the missiles missed, achieving a gun's kill required the pilot to fly extremely close to the target, struggling with heavy stick forces while looking through a tiny, cluttered canopy. Yet, understanding the weaknesses of the MiG-21 did not magically remove its threat. The operational reality of the aircraft extended far beyond its aerodynamic dogfighting traits. Its true power lay in its logistical footprint. The Soviet Union planned for a massive, high-attrition war in Europe. They did not want delicate, temperamental aircraft that required pristine runways and air-conditioned hangars. The MiG-21 was built for the dirt. Its rugged landing gear and low-pressure pneumatic systems meant it could operate from poorly paved secondary roads or rough grass strips. The maintenance philosophy was equally brutal. Rather than designing components to last thousands of hours with careful maintenance, the Soviets designed components for a short, violent lifespan. The Tumansky engines frequently required complete overhauls or total replacement after just a few hundred flight hours. To Western logisticians, replacing an engine that frequently was madness. To the Soviets, it was simple math. In a full-scale European conflict, the statistical likelihood of an airframe surviving more than a few dozen combat sorties was virtually zero. Why over-engineer an engine to last 2,000 hours if the jet was going to be destroyed in its first 50? This philosophy of mass and disposability meant the Soviets could churn out airframes at a staggering pace. Over 11,000 MiG-21s were built in the Soviet Union, Czechoslovakia, India, and China. They flooded the arsenals of the Warsaw Pact and were exported to virtually every Soviet-aligned nation on the planet. The brutal math of warfare dictated that NATO pilots, even in their technologically superior aircraft, would be severely outnumbered. An American F-4 might be able to defeat 2 or 3 MiG-21s, but what happens when the 4th, 5th, and 6th appear on the radar scope? This numbers game dictated Western fighter design for an entire generation. The existence of thousands of MiG-21s was a primary driver behind the development of the F-15 Eagle and the F-16 Fighting Falcon. The United States realized they needed aircraft that could maintain high energy states in a dogfight, completely outclassing the Delta Wing's energy bleed, while carrying enough missiles to handle the swarm. As the decades rolled on, the inherent limitations of the MiG-21's original design began to catch up with it. By the 1990s, the tiny radar cone and poor situational awareness were no longer just compromises, they were death sentences in an era of advanced beyond visual range combat. But the airframe proved remarkably stubborn. How do you keep a 1950s aerodynamic tube relevant in the 21st century? You do it by acknowledging the airframe's limitations and overhauling the systems that matter. Programs like the Indian Air Force's MiG-21 Bison upgrade attempted to drag the brutalist machine into the modern era. They could not change the physics of the translating shock cone to fit a massive radar, so they completely redesigned the avionics architecture behind the scenes. They fitted the aircraft with a lightweight, multi-mode radar system, integrated advanced data links, and most importantly, paired the pilot with a helmet-mounted sight and R-73 high-off-bore sight missiles. This created a bizarre operational paradox. A pilot sitting in a cramped analog cockpit designed during the Eisenhower administration, flying an airframe with the aerodynamics of a lawn dart, but able to look over his shoulder, visually target a modern multi-role fighter, and fire a sophisticated heat-seeking missile without ever pointing the nose of his aircraft at the enemy. It was a terrifyingly lethal combination that proved the fundamental durability of the MiG's core philosophy. Put a weapon in the air quickly, cheaply, and let the systems handle the rest. The legacy of the MiG-21 is not defined by its comfort, its range, or its electronic sophistication. It is defined by its absolute adherence to a specific strategic doctrine. The Soviet engineers did not build a bad aircraft. They built a perfectly optimized solution for a warfare model that prioritized mass, ground control, and overwhelming numbers over individual pilot agency. They built a machine where every bolt, every aerodynamic compromise, and every ergonomic failure was a calculated price paid for supersonic speed and mass production. The translating shock cone that choked the avionics was the same cone that allowed a cheap turbojet to propel a thin triangle of metal to Mach 2. The tiny delta wings that bled energy and caused horrifying landing speeds were the same wings that allowed the airframe to be manufactured by the thousands with minimal structural complexity. It was an aircraft where the pilot was heavily compromised, but the doctrine was flawlessly executed. In the brutal math of aerial warfare, the MiG-21 proved that sometimes simplicity and sheer volume have a quality all their own. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.